Welcome to sections 5.2 and 5.8. I'm going to do the notes a little differently this time, and I'm just going to put them kind of in a slide per column so that it's a little easier to follow. So I'm going to start with the zeros and intercepts column, which is the first column to the left, and we're going to be graphing polynomials, and I want to get some basic ideas as to what's going on. Okay, we're going to give you these factors in number 1. So we have x minus 2, x plus 3i, and x minus 3i. And we want to know what are the solutions. So I'm going to go back to chapter 4 again. And if we said if x minus 2 is a factor, we could set x minus 2 equal to 0 and solve. And we would get a solution or an intercept of 2. Okay, and basically as you're looking, solutions are the same thing as the intercepts. So we have one intercept or solution of x equals 2, and we're going to do the same thing. If I have an x plus 3i equals 0, when I subtract 3i to move it to the other side, I get that x is a negative 3i. So there's our second solution. Now, it's an imaginary solution, which means you're not going to see it on a graph. So it's not going to intersect the x-axis, but it is still considered a solution. Okay, third one, if I have x minus 3i equals 0, I'm going to add 3i to both sides. Therefore, I get that x is 3i. Okay, now we've talked in previous sections that if you have a negative I, you will also have a positive I because they come in conjugate pairs. So as we think about a graph, again, the only solution that you're going to see on the x-axis is x equals 2 because that's the real 0. The other two are imaginary, therefore you're not going to see them. Okay? As you look at question number 2, we've got x plus 1 squared, x minus 1, and x minus 3. Now, this squared is what we call a multiple 0. So as you're looking at this, this says there are 2 zeros here, a 0 with the x minus 1 and a 0 with the x minus 3. Therefore, there's a total of 4 zeros. One of them is a repeated 0, and so we're going to find that first. When I give you x plus 1 squared, we don't have to worry about the squared because I'm just setting the parentheses equal to 0. So I can say x plus 1 equals 0, and if I subtract 1 on both sides, then x equals negative 1. Now again, we call this a repeated 0 because it happens twice. Okay, so this 0 occurs twice, and we will talk in a minute about what that graph then looks like. The second 0, I apologize. The second factor, x minus 1 equals 0. When we add 1 to both sides, x equals 1, so we have another 0 of 1. And last but not least, x minus 3 equals 0, so when I add 3 to both sides, I get that x equals 3. Now let's just talk in terms of the graph for a moment. When you have, as you look at a graph, and I'm not going to go too in depth yet, but here as we look at it, I know at 1 I'll have a 0. At 3 I'll also have a 0, and then at negative 1 I'll have a 0, and that happens twice. Now we're going to talk about mixing in this leading coefficient and what does the graph look like in a minute when we get to the back side of your frame. But as we're looking at it, what's going to happen is that this repeated 0 will look kind of like a parabola. And I want to go back a second to vertex form, and I'm going to change my color so that you can see it a minute. But if I would have given you, and I'm just going to put it up here, y equals x plus 1 squared, I'm going to put a plus 0 here in a minute. But this was vertex form, and we originally knew that the a value here is positive, so my graph opens up, and the vertex occurs at the point negative 1, 0. Now, it works exactly the same way, even with other multiple factors. So this will be kind of like a parabola that opens upward. But then what happens is because I have other zeros, it's going to go through that 0 and then come back around, and touch the other 0 as well. Now, I don't know the exact picture because I don't have my graphing calculator on me, but the general idea is that when I look at this, I know it's squared, and like a parabola that was squared, it's going to be determined whether I open up or down, and then it'll follow a path from there. Okay, and we're going to talk about that in a little bit, but this is kind of the general idea. The last one, talking with factors, is we give you the solutions, and we want you to write the factors. And we've done this in previous sections. So if I give you a 0 of -4, then I have x plus 4 as a factor. And if I have a 0 of 2, then I have x minus 2 as a factor. Okay, now we kind of touched on it right above in number 2, but a graph touches the x-axis. It means there is an even degree. And basically an even degree for the factor. And I want to kind of put it that way because it works the same way. But what we're saying is basically the factor occurs 2, 4, sorry, I'm doing this too late at night, 2, 4, 6, or 8 times. When it crosses, like the ones you saw in number 2, it crossed at 1 and it crossed at 3, those only happened once. And so we're going to say they happen an odd number of times because they could happen 1, 3, 5, or 7 going through. Okay, and what we're going to do is practice a few more of those so you can see. But I wanted to at least give you this idea. And this, again, is a general picture. Okay, so let's move to. Okay, looking at this, I've written a note for you. The local maximums, minimums, and zeros. When it comes to your graphing calculator, because I'm at home and I don't have my software for the calculator, what I'm going to do is do this in class together. Plus, we're going to need to walk by it step by step. If you don't have a graphing calculator, please see me now. You need to get a contract for a graphing calculator, and don't forget it costs $20. It is so important because in this section you have to have the graphing calculator to be able to do these questions. Okay, let's move on to the next column with substitution. The direct substitution and synthetic substitution. Direct substitution is something you're used to seeing, where if I give you a function x squared or x to the 4th plus 2x cubed plus 3x squared minus 7, and I'm asking you to find f of 2. What that means is take the 2 and plug it in for the x. So f of 2, and we did this in chapter 1, we're just going to add more to it. We say take 2 to the 4th plus 2 times 2 cubed plus 3 times 2 squared minus 7. And all we want you to do is plug it in your calculator, see what type of answer you get. Oh, and I apologize, that's a -2 in your notes, so I better switch it in mine. What you end up getting then is a value of 5. And so you'll want to plug this in your calculator and make sure that you're able to get a value of 5. We're going to go one more using direct substitution. If I ask you in the second one, what is f of -3, we take 4 times -3 squared to the 4th. Let me move that. We'll erase this. To the 4th minus 6 times -3 cubed plus 3 times -3 squared minus 7 times -3 and then a minus 5. Now what you'll notice is when I did the negatives, you really want to put it in parentheses or your calculator doesn't understand when to make it an even exponent, which turns it positive, or an odd exponent, which keeps it negative. But you plug this in your calculator exactly as is with all the parentheses, and you should get a value then of 529. Okay, so pause it a second and give it a shot to make sure you're able to get that. This synthetic substitution basically brings us back to synthetic division, and we're going to get a similar answer. Okay, so what I want to do is if we gave you the value of 2 for synthetic division, we'd put 2 outside the box and we'd put our coefficients. 5 is the cubed term, 3 is the squared term, -1 is the single x term, and then 7 is our constant. Okay, we drop the 5. 5 times 2 is 10. We then add it to 3. 10 plus 3 is 13. 13 times 2 is 26. When you add it to negative 1, you get 25. 25 times 2 is 50. When you add it to 7, you get 57. Now, here's one thing about synthetic substitution. This remainder is exactly the same thing as if I would have plugged f of 2 in. If I would have taken 2 and directly substituted it in, I would have also gotten 57. So pause a minute, try that. Now, since you found that this was 57, what we are trying to say to you is it's easier to do synthetic substitution where you don't have to deal with exponents than do the direct substitution where you have to know what negative 3 to the 4th is or negative 3 cubed is and then be able to multiply that number by 6. By using synthetic substitution, you don't have to deal with exponents. So let's try one more. I'm taking a negative 1 and I'm going to plug it into the function negative 2x to the 4th, negative 1x cubed. You'll notice I don't have an x squared, so I'm going to put in a 0 for my x squared. And then I have a 4x and then minus 5. Okay? We drop the negative 2, multiply that by negative 1, you get a positive 2. 2 and negative 1 gets 1. 1 times negative 1 is negative 1. Negative 1 plus 0 is negative 1. Negative 1 times negative 1 is 1. When you add it to 4, you get 5. 5 times negative 1 is negative 5. You end up getting then an answer of negative 10. So basically, as you look at this, if I plug a negative 1 into the g function for x, I should get negative 10 as an answer. Okay? So that's the front page, and we're talking again a couple of keys. The graphing calculator stuff I do want to do together. So what we're going to do is we're going to flip to the back side of the frame, and I'm going to show you two different things. All right, we're going to talk about end behavior with functions, and basically what we're asking you is as we graph this, what's going to happen on the ends of each graph? Where is it going? And I'm going to say it in words, and then I'm also going to show it to you. Notation is going to be the hardest part about this, okay? We have odd functions, and you have two options. One, where the leading coefficient, which is the number in front of the degree term, so in front of the highest exponent, one where it's positive, okay? And then we're going to have one where the leading coefficient is negative. Okay, odd functions means something that starts with an x cubed or an x to the 5th or an x to the 7th, anything like that, where the degree of the polynomial is an odd number. If it's positive, it's going to be S in shape, and it's going to start low and end high because it's increasing. If it's negative, it's going to start high in an S shape and go downward into the negative area. Okay? Now, what we're going to do is write the end behavior, and we're going to do it in a couple of ways. You will always have two mathematical expressions in order to be able to talk about end behavior. We're going to look once as we go to the left. So as I look to the left is going to be one way. And the way we say go to the left is we say as x approaches. And if we go left, we keep getting more negative. The biggest negative number we know is negative infinity. Okay, so as x goes left all the way to negative infinity, the question is what happens to our graph? And our graph we call f of x. Okay, it's our function. What happens to our function? So as I go to the left, my function goes down, and it goes down to negative infinity. So we say f of x goes to negative infinity. So if you're reading this in words, it says, as I go left, my graph goes down. Okay, this is what it means. The problem is we have to have this notation right here. That's something you have to have when it comes to test and quiz time. Okay, so let's look at the second one. Now we've gone left, now let's go right. So as I go right means as x gets to the biggest possible number I know, which is positive infinity, the question is what happens to my graph? So as I go to the right, my graph goes up, which means f of x goes up to the biggest number I know, which is positive infinity. Now you could put the plus sign for positive if you want, but you won't see me do that. So what this says is as I go right, my graph goes up. Okay, and there again is a difference between mathematical notation and just wording. And so I'm okay with you describing it to me as left and up or right and down. The problem is on the quiz and the test, we need the mathematical notation. And we're going to give you some of those graphs. Okay, we're going to do it again. Let's go to the left first. So if we go to the left first, we says as x goes, and the smallest number we know to the left is negative infinity. The question is, where is my graph going? Well, as I go left, my graph goes up. So f of x goes to positive infinity. In the second one, as x goes right, which is the most positive, so a positive infinity, my f of x goes down. As I go right, my graph goes down, therefore f of x goes to negative infinity. Again, I'm only writing these ones this time because you have to be in what we call function notation or end behavior notation. Okay, so this is the odd functions. That's that first column. Now we're going to go into the last column, which is the even functions. Okay, we still have two choices again. We can have the leading coefficient, and I'm going to shorthand it this time, be positive. Okay, or we could have the leading coefficient be negative. All right, so here we go. As we go positive, even functions, think about it as x squared, x to the fourth, x to the sixth. Now think about x squared. When the leading coefficient, when the number in front was positive, the graph opened up. Same thing as you get higher in even degrees. It opens up. Some of them will be parabolas, so I'll do one that's in parabola form. Some of them will be W-shaped, and I'm going to do that in the negative form. Positive opens up, so we can see it open up. Negative opens down, so I'm going to show you that W form as well. The higher the degree, the more turns it gets. Okay, the more turning points it has. So let's again describe end behavior. And let's go to the left first. All right, as x goes, the most left point is negative infinity. F of x goes up. We say as we go left, it goes up, so it goes up to positive infinity. Second one, as x goes to the right or to positive infinity, my graph, f of x, again, you can see it goes up. So it goes to positive infinity. Last one, if it's negative, again, we're going to say the same thing. As I go left, so as x goes to negative infinity, my graph, if you look, as I trace it left, it goes down, so it goes to negative infinity. And last but not least, as x goes right to positive infinity, f of x, as I trace to the right, f of x goes down to negative infinity. Now, one thing to keep in mind, something that I'm hoping you're noticing, with even functions, you either both go down or you both go up. But with odd functions, they vary. One might go up and one goes down, and it depends on if your leading coefficient is positive or negative. Okay, so those are things to keep in mind. But again, the graphing stuff we're going to work in class so that I can show you how to use the graphing calculator. I'm also going to give you a sheet of paper that tells you how to find all of that stuff with your graphing calculator. But for now, this is kind of the general idea for sections 5.2 and 5.8. Thanks for watching.